Now we discuss. Okay. Welcome you all in this lecture on fixed point theory. So in this lecture, I shall consider. I will give you only a flavor of fixed point theory, and we will prove only a one fixed point result that is known as Banach contraction theorem or Banach contraction principle. Okay, and I just will present you few examples or few applications of Banach contraction theorem, and we will present the Banach contraction theorem. So, okay, so first question is what is the fixed point theory, or what is a fixed point? So, let us take here is suppose X is any non-empty set and T is a self map from X to X. Okay, so this keep in mind the T is a map from X to X. It is not a map from X to Y. Okay, then a point X bar in X is said to be a fixed point of T if T of X is equal to X bar. Okay, so a point X bar in X is said to be a fixed point of T, if the image of X bar under T is itself X bar. And that's why we are considering T is a map from X to itself. Now, for example, we can consider several here. Let us take X is equal to set of all real numbers. Okay, and first we take T is a map from X to R, X to X, okay, which is defined as Tx is equal to X plus A for some fixed number A which is not equal to 0. And then you can see that you cannot find any X bar, okay, you cannot find any X bar such that X bar is equal to Tx bar. Because when you whatever the number you take X bar here is you will get X bar plus some constant which is not equal to 0. So you cannot find any X bar, okay, such that Tx bar is equal to X bar. So this map which is defined as Tx is equal to X plus A does not have any fixed point. Okay. Now if we define the map T from X to X in the following way, that Tx is equal to 1 over 2x. Then you can see that if I take X is equal to 0, so this is equal to 0, this is equal to 0. So it means that T has a fixed point, that is X is equal to 0. And that is the only fixed point. So you can say that this map has a unique fixed point, and that is X is equal to 0. Now we define the same function we define the function T from X to itself in the following way, that Tx is equal to X square. Then we can see that X is equal to 0 and X is equal to X is equal to 1 are the fixed points of T. Okay, so there are two fixed points of T. And now if we define the mapping T as Tx is equal to X, and then we see it's every point. Okay, so whatever is a point you take, you will get that would be a fixed point under this mapping. So T has infinitely many fixed points. That is, in fact, every point of X is a fixed point of T. So here we have seen that a map can have a unique fixed point, cannot have any fixed point, can have two fixed points, can have more than two fixed points, can have infinitely many fixed points. Okay. So take before going to basically our main aim is to show that under what condition we will have a unique fixed point. Okay, that is the main result, and that is known as Banach contraction theorem. So we want to discuss the Banach contraction theorem, which says that every contraction map defined on a complete metric space has a unique fixed point. So before going to the contraction, the definition of the contraction of a map, let us have some other examples. So if we consider X is equal to R2 and T is a map from X to to itself, which is defined as t xy is equal to y over 10 and x over 10, okay, for all xy in R cross M. Then xy is a fixed point of t if and only if x is equal to y upon 10 and y is equal to x upon 20, x upon this is 20 here, so x upon 20. That is if and only if xy is equal to 0 0, and therefore the fixed point of t is 0 0. So the fixed point of t is the fixed point of this map is the point only 0 0. Take some non-trivial example. So for non-trivial example, we consider the space x is equal to set of all continuous functions defined on a closed interval AB, and t is a map from x to itself, which is defined as tux is equal to half the integral from 0 to x us ds for all u in CAB and all x in AB. Then a fixed point of t is a solution of the integral equation, this one, ux is equal to 1 over 2 integral from 0 to x ux dx. So you see that it's very interesting that a fixed point of this integral equation, okay, and is a solution, the fixed point of this operator t, the fixed point of this operator t is the solution of this integral. Basically, the fixed point of t of this is what? Of u of x. So we can write u of x is equal to this, and this is what? This is same as this one. So you can check very easily. It is clearly mentioned that the mapping defined in this way, if this has a fixed point, that would be a solution of this integral equation. Now you can simplify this differentiating with respect to x. This becomes a linear differential equation, du upon dx is equal to 1 upon 2 ux with the initial condition u0 is equal to 0. This differential equation has a general solution, ux is equal to a raised to the power a into exponential e raised to the power x upon 2, where a is a constant. By using the initial condition, we obtain 0 is equal to u0 is equal to a of 0 is equal to a. Therefore, ux is equal to 0 for all x is the solution of the differential equation, this one, which is a fixed point of t, and that is ux is equal to 0 for all t is the solution, is a unique fixed point of t. So you can see that a fixed point of this is also a solution of the fixed point of this, and the fixed point of is the solution of the solution of this integral equation. Now we can take here is another example. As a remark, as we have seen in the previous example, in the example 6.1, that a mapping may not have any fixed point, it may have a unique fixed point, it may have more than one fixed point, or even infinitely many fixed points. Let x is equal to r and t is a map from x to itself, defined by tx is equal to 1 plus x whole raised to the power 1 over 3. Then finding a fixed point of t is equivalent to solve the equation x cube minus x minus 1 is equal to 0. How can you do this? You can take x, you take on the other side, so x is equal to x cube, okay. So you take x plus 1 on the other side, this you take on the other side, okay, and then take the cubic root both the sides, so x is equal to 1 plus 1 over x. So if this has a fixed point, and this is equal to x, okay. So if t has a fixed point, then it is equal to x, and then take the cube both the side, you will get this one, and therefore you can see that a fixed point of this map, is the solution of this. Not only this, you can define some other fixed maps which would have a you can define another map in such a way that the fixed point of that map would be a solution of this this equation. Basically, now we come to the main definition. So let us take X be a metric space and T is a mapping from X to itself. And a mapping from T itself is said to be Lipschitz continuous if there exists a constant alpha is greater than 0 such that the distance between Tx, Ty is less than or equal to alpha times distance between X and Y for all X and Y in X. Okay. In other words, you can see that if Y, okay, here this means that T of Y lies in the, you can see that the distance between this and this is less than. Now, if alpha is equal to 1, then you can take here this is less than or equal to dxy. So this is less than or equal to, so if the alpha is equal to 1, this mapping is called non-expansive. If this alpha lies between 0 and 1, okay, open interval 0, 1, not 0, not 1. So it is 0 and 1, then we say that T is a contraction mapping. Okay. If the distance between Tx and Ty is strictly less than the distance between X and Y for all X is not equal to Y, then T is said to be contractive. Okay. And this alpha is called Lipschitz constant of T. Now, what is the meaning of this one? What we are doing? We are doing that basically, if you have here is this means for all Y. So you take this means all Y lies in the open sphere with center at X and radius R. So suppose this is your open sphere, okay, with center at X and radius R. And now we take this one in this. This is your the image of this one is going to this one. So when we multiply it by this one, it means that it is shrinking. Okay, so we will have the Tx. So this is this is the open ball with center at T of X and radius S. But this because of the multiplication from alpha, we are shrinking this open ball and we are getting only this image. So this is the way. So by multiplying alpha, we are shrinking the distance between T of X and T of Y by the constant alpha, because alpha lies between 0 and 1. So a contraction shrinks the distance by a uniform factor alpha for all pair of points. Okay. Now, let's have some remark. A remark says that if X is a metric space and T is a contraction with constant alpha lies between 0 and 1, then for any natural number n, Tn is a contraction with constant alpha n. This you can prove very easily, so no problem. And let X be an element in capital X. For large alpha R is greater than 0, the image of the open ball with center at X, radius R under T, okay, is a subset of the image of and lies in the open ball with center at X and radius R. But they may not be equal. Also, for any natural number n, Tn SRX is a subset of Tnx, where S is equal to Rn alpha. In particular, you can see that the open ball, okay, the image of the open ball lies in strictly lies inside the open ball with center at x and radius. As we have seen here is the image of this. The image of this lies in the open ball. Okay, strictly lies. It is not equal to this one. Strictly lies inside this open ball. So this means this one. And every contraction mapping is uniformly continuous, because we have already seen that every here is if this is Lipschitz continuous, so Lipschitz continuous is more than the continuity. So every Lipschitz continuous function is continuous. Okay, and similarly, not only this, every contraction mapping is uniformly continuous. Now, another remark, we say that it is clear from the definition that every Lipschitz continuous function is continuous and every contraction mapping is contractive. But the converse assertions may not be true. For example, consider the metric space 0, infinity with the usual metric and the mapping T defined by T of x is equal to 1 over 1 plus x square. Then T is contractive but not contraction. Now finally, we have our main result. We say that, which is known as Banach contraction theorem or Banach contraction principle. It is very simple. The importance of this result is that it is very simple and there are not many hypotheses. Only the thing is that every contraction map defined on a complete metric space X to itself has a unique fixed point. So you have only two things. The space, the mapping is contraction, which is defined on a complete metric space. So you need only two things. The completeness of the space and contraction mapping. Okay, with these two, you have a unique fixed point. As you know that in mathematics, uniqueness is very, very important. Now, we prove this theorem, and basically the theorem based on the construction of a sequence. It is a constructive proof, and not only this, you can also use this theorem. By using the proof of this theorem, you can also find a fixed point. Basically, this theorem gives you the existence of unique fixed point, but by using the theorem, okay, you can, by using the proof of the theorem, you can calculate the fixed point. Okay, we will see how it is. So we construct a sequence xn by the following iterative method. So how we can choose any point x naught in x, okay, which is not equal to t x naught. Otherwise, x naught would be a fixed point of t. So then there is nothing to prove. So we define, okay, so we are starting from any point x naught, and then we are defining that the image of x naught is equal to x1. Okay, now we get this x1. Of course, if t of x1 is equal to x1, then x1 would be a fixed point. In other case, we can define x2, which is equal to the image of x1, and then again, if x2 is equal to tx2, so x2 is a fixed point. So we can continue in this way. So we can continue this way in the xn is equal to t xn minus 1 for all natural number n. So this way we defined a sequence. That this is the way to define a sequence, and now we claim that this sequence of points of x is a Cauchy sequence. First we prove that this is a sequence of points in x is a Cauchy sequence, and x is complete, we are assuming, so it will converge to a point, and we will see that that point is a unique fixed point. Okay, so let's say here is so since x is a contraction mapping with constant alpha lies between 0 and 1. For all p runs from 1 to infinity, we have dxp1 dxp is equal to d, because the txp is equal to txp plus 1. Okay, by our rule, by which we have defined the sequence. So by using the sequence, this xp is equal to txp minus 1, And because t is contraction, so this is less than or equal to alpha times dxp minus 1. Okay, and then again use the xp is the txp minus 1, and this xp minus 1 txp minus 2, and again t is contraction, so this is equal to, this is your alpha, so this is alpha d xp minus 1 xp minus 2, so alpha and another alpha, so alpha square. Continue in this way, we will get this, the whole thing is less than or equal to alpha p d x1 x0. Now instead of taking xp plus 1 xp, now let's take m and b any positive integers with n is less than m. Then by the triangular inequality we have dxm xn, so it is less than dxm xm minus 1, because n is less than m, so m minus 1, and then m minus 1 m minus 2, continue up to xn plus 1 xn. This is what? This is less than alpha times m minus 1 dx1 m from here, because here is this is your p xp, then this is alpha raised to the power p. So here is you have xm minus 1, so you have xm minus 1 dx1 x2. This is, then you have alpha raised to the power m minus t, and this is your alpha raised to the power n mp. Now from here you can take alpha n is common, then you will get this one. But this is what? This is equal to 1 over 1 minus alpha. So we can write it this way. And now since alpha, the limit of this is equal to 0 and this is a fixed number, okay, the right hand side of the above inequality approaches to 0 as n tends to infinity. It follows that xn is a Cauchy sequence in x. Since x is compact, there exists x bar in x such that xn converges to x bar. Now we claim that this limit point x bar is a fixed point of t. Now since x is a contraction mapping from the triangular inequality, we have tx bar, the x bar dx bar, the distance between x bar and dx bar is less than or equal to this thing by the triangular inequality. Okay, now here is txn is equal to txn minus 1 by the definition. So it is, and then here we can use because t is your ellipsis continuous, so this is less than or equal to alpha times dxn minus 1 x bar. Okay, and since the sequence converging to x bar, so this converges to 0 and this converges to 0, the whole thing converges to 0 as n tends to infinity. It means that and so this converges to 0, and hence and this is of course is greater than or equal to 0, so this is equal to 0 and this is holds, and therefore tx bar is equal to x bar. Okay, so this way we can prove that x bar is a fixed point of t. And not only this, now we show that the fixed point of t is unique. So suppose to the contrary that x, y are two distinct points of t, then tx is equal to x and ty is equal to y. Since t is a contraction mapping, we have this one dx is equal to this, because tx is equal to this, so we can, and now by using the contraction we can, and this is strictly less than dxy. So dxy is strictly less than dxy, it is not possible, and therefore x must be equal to y. So this is the Banach contraction theorem. Okay, so then let us take here is as I mentioned that we are considering only only two hypotheses in the Banach contraction theorem. One is x is complete and other is t is contraction. Suppose f is not complete, okay, then we will see that t may not have a fixed point. For example, consider x is equal to the open interval 0, 1, and consider t is a map which is defined as dx is equal to 1x upon 2. And then of course because x is equal to closed open interval 0, 1, it is not complete, and you will see that t does not have any fixed point in x, because the fixed point of t is 0, but t0 is not in x, so it would not have a fixed point in x. The second example, we see that if t is not contraction, if T is not contraction in the Banach contraction theorem, then the theorem may not hold good. You can see that if T is not contraction, then it may not have a fixed point. For example, consider the complete metric space X is equal to close interval 1 to infinity. So this is a complete metric space with respect to the usual metric, and define a mapping T like the Tx is equal to x plus 1 over x. Then T is complete, but we can see that x is complete, but T is not contraction. How it is not contraction? You can see that Tx minus Ty is equal to, you can simplify that it is equal to x plus 1 over x minus x minus 1 over x, and then you take mod of x minus y is outside, and you will get 1 minus 1 over x minus y. And this term, okay, so this whole term, this term is less than 1, okay, so this term is less than 1, okay, so this whole thing is less than mod of x minus y. So it means that there is no alpha, there is no fixed alpha, because if we consider this as a alpha, so it means that there is no fixed alpha, but here is alpha is depending on x and y. So we cannot find a fixed alpha which will work for all. So we can see that there is no alpha such that Tx minus Ty is less than or equal to alpha times mod of x minus y. So this is less than or equal. So T is contractive, but it is not a contraction, and T does not have any fixed point. So you can see that there is no fixed point of the mapping T. So we can see that T does not have any fixed point. Now we have another example. So before going to see another result, we have to see the following example, which says that if X is a complete metric space and T is not a contraction mapping, okay, but the T square, the composition of T with T is contraction, okay. T is not contraction, but T composition, this is contraction. Even then, T has a fixed point. So here is the important thing, that if T is not contraction, but X is your complete metric space, but the T squared, the composition of T with itself is contraction, but T may not be contraction, even then T has a fixed point. Now let us see, here is we consider X is equal to R with the usual metric space, and T is defined as Tx is equal to 1 if X is rational, Tx is equal to 0 if X is irrational. Then T is not continuous, is well known, and hence not a contraction. But T square is equal to T of X, so it is equal to T of 1. So T of 1, because the rational number, it is equal to 1, so it is 1. Similarly, T square X is equal to T of 0 is equal to 1 again if X is your irrational number. So T square, now then T square is a contraction mapping, but both T square is a contraction, but both T square and T have the same fixed point, that is 1. Now from this example motivates us to present the following result. What is the result? Result says that let X be a complete metric space, T a mapping such that for some integer n, okay, Tm, which is the composition of m times, so is a contraction mapping, then T has a unique fixed point. Okay. So if T is not a fixed, T is not a contraction map, but Tm for some integer m is a contraction mapping and X is a complete metric space, even then T has a unique fixed point. Now from the Banach contraction theorem, because Tm is a contraction mapping, so Tm has a unique fixed point. Let us take Tmx is equal to x. then we can write Tx is equal to, you operate T both the sides, so Tx is equal to T, Txm, so it is equal to Tm, you can take outside, T of x. Okay, it means what? It means that Tm, Tx is equal to Tx. So it means that Tx is a fixed point of Tm. So Tx is a fixed point of Tm. Now since the fixed point of Tm is unique, okay, since because Tm is a contraction mapping, okay, Tm is a contraction mapping and x is complete, so it would have a unique fixed point. So Tm would have a unique fixed point. So this has a unique fixed point. So x is a fixed point and Tx is a fixed point. So fixed point is unique. So Tx is equal to x. So it means that x is a fixed point of T. To prove the uniqueness, we assume that y is another fixed point of T. Then Ty is equal to y, and so Tmy is equal to y. Again, by the uniqueness of the fixed point of Tm, we have x is equal to y. Hence, x is a unique fixed point of T. So this way, we can prove that if X is a complete metric space and T is not necessarily contraction, but Tm is contraction, even then T has a unique fixed point. And I stop over here, and in the next talk, we will see that if T is a contractive map, not necessarily contraction, okay, then what will happen? Okay, so then we stop over and we will see later.